In this presentation, we're going to explore electromagnetic induction, which is basically a situation where a changing magnetic field that passes through a coil can induce a voltage and also a current in the circuit. So we're going to basically look at a couple of different questions, and we're going to answer those questions by using the Phet simulation. So here's the Phet simulation, which is actually a Java file, and a lot of, like I said before, a lot of computers will not allow you to open Java files and use them. So that's why we're going to go through this together as a group. So in the left-hand corner of the simulation, we're going to use the pickup coils, click on the magnet, move it slowly back and forth, and what happens to the brightness of the bulb as the magnet moves quickly as compared to slowly. So here's the pickup coils right here, and you'll notice there's also a light bulb. And so I'm going to take my magnet and I'm going to hold on to it and I'm going to move it back and forth. And you can see that the bulb lights up when I move it back and forth. Now notice what happens if I move it faster, back and forth. The bulb is brighter, right? And so when I move it faster, there's a greater change in the magnetic field strength that passes through this coil, because right now the magnet's further away, right? So there's not a lot of magnetic field strength, and as I move it closer, there's magnetic field, and as I go back, there's magnetic field. But if I go faster, there's a bigger change in the magnetic field that passes through that coil, and therefore I get a bigger voltage and I get a bigger current that's going through that light bulb. Remember, the brightness of the bulb is related to the current. Now I can change the number of loops in the pickup coil and move the magnet back and forth. I have to try to move it about the same speed, and I can see what happens as I repeat it for 2 and 3 coils. And let's look at what happens to the brightness of the bulb. So I'm going to change the number of loops in the coil here to be 1, and I'm going to move it back and forth, and let's take a look at what that light bulb does. So I'm going to go back and forth, right? Trying to go at about the same speed. So only 1 loop. If I make it 2 loops and I go back and forth, hopefully you can see that it's brighter with 2 loops. And then if I go to 3 loops and I go back and forth, those lines are even longer, right? So it's even brighter. So the more coils that you have, when you change the magnetic field, so a single coil here does induce a voltage when you have a changing magnetic field, but the more coils that you have, the greater the voltage that will be induced in that loop, and of course the greater the current will be as well. So now we're going to click on the tab that's labeled Transformer, and we will see an electromagnet and a pickup coil with a bulb. The electromagnet is basically just like a bar magnet, and we're going to use that electromagnet similar to what I did here with the regular magnet. What happens to the indicator bulb brightness? Make sure the indicator bulb is chosen. As more loops are present in the electromagnet, what does this tell us about the making a strong electromagnet? All right, so the other thing, so I'm going to reiterate those questions, but if the magnet is not moving, the light bulb doesn't light up, right? Because you have to have a change in the magnetic field that passes through the coil. All right, so I'm going to click on electromagnet, and actually, okay. Here we go. We're going to click on Transformer, and as I take my electromagnet, it produces a magnetic field that's basically just like a bar magnet. So if I move this back and forth, just like before, a changing magnetic field is going through that coil that has the indicator bulb on it, and voltage is induced. If I stop moving my electromagnet, because basically an electromagnet is behaving just like a bar magnet, then there's no voltage that's induced. If I change the number of coils on my electromagnet, so right now there's 4 coils, so let me move it back and forth again. I'll try to go at about the same speed, right? Back and forth through the coil. If I change this down so that it only has 1 loop and I go back and forth, notice what happens to the indicator bulb. It's not as bright. So what does that tell us You know, as more loops are present in the electromagnet, what does this tell us about the strength of the electromagnet? So if I have more loops of coil in my electromagnet, so when I put it back to 4 here, it produces a stronger magnetic field, and if I have a stronger magnetic field and I move it back and forth through that pickup coil with the light bulb, there's a greater change in the magnetic field strength in here, and because of the fact that it's a larger magnetic field, and I get a brighter bulb. So if the electromagnet is not moving, of course, the bulb does not light up. So we have to have a changing magnetic field strength through that coil of the indicator bulb to actually get the bulb to light up. All right, we're going to keep the number of coils fixed in the electromagnet, and we're going to adjust the number of coils on the pickup coil by using the controls, and then we're going to move the electromagnet back and forth. What happens to the brightness of the bulb when the pickup coils are changed? All right, so this is basically just like the last one that we did with the bar magnet. So here's my pickup coil. I'm going to start off with just one loop, and I'm going to move this back and forth, and we can see, I try to go at the same speed, we can see the brightness of the bulb. If I add, let's say if I make this 3, and increase it and I move it back and forth, the bulb is much brighter, right? So same reasoning as before, you're going to get a larger voltage induced in your pickup coil where you have this indicator bulb if you have more coils of wire, and of course the bigger the change in the magnetic field strength that passes through there, the larger the voltage will be and the larger the current. We're going to place the electromagnetic coils so that they are directly inside the pickup coils, and then we're going to change the current to AC. So I'm going to take this, I'm going to put it inside, and once I stop moving, of course, nothing happens, but I'm going to change this. Instead of being a DC battery, which produces current in only one direction, I'm going to make it AC. And you'll notice that the light bulb is now lighting up. So what happens to the magnetic field? Does it stay constant or is it changing? And of course the answer is when you change the pickup coil, when you change the source to AC, that produces oscillating current in the coil. I'm going to go ahead and take it out for a minute. Oop, wrong one. Go ahead and take it out for a minute. Right, so the current is oscillating back and forth. That's what AC means. And therefore the magnetic field is switching direction, right? You can tell the compass needles are changing direction there. I'm going to go ahead and I'm going to increase the strength of that, and now I'm going to put it inside, and I can see that the light bulb lights up. And I can also change the frequency at which this oscillates, and if I get it fast enough, the light bulb is really lighting up there, and of course I'm having a greater change in the magnetic field strength. So our light bulbs that we have in our house are connected to AC, and of course they don't fluctuate like this because it's oscillating so fast that we can't actually see it. But again, a changing magnetic field from that AC source is passing through that coil, and as a result I have an induced voltage. I don't even have to have it inside the coil, I can just have it nearby, and there's still a changing magnetic field strength through that center, and it's inducing this oscillating current in the pickup coil. And we did adjust that voltage to a maximum, and we saw that the brightness increased. So if I change the brightness of the voltage maximum to a smaller value, it's not as bright because I don't have as big of a magnetic field that's produced, and it's not going to have as big of an effect. And if I change how fast it's fluctuating, that's also not going to have as big of an effect, right? Here the coils are not fluctuating as quickly, and so the current is less because the magnetic field is not changing as drastically. So we see that in order to induce current in a light bulb that's connected to a loop of wire and it's not connected to any voltage supply, I have to have a changing magnetic field that passes through the loops of that pickup coil. And it turns out that an electric generator works in this way, and we can see that by clicking on the generator, and we'll see a magnet that's attached to a wheel. When we turn on the water faucet, we can see what happens, and then we can adjust the water so that it comes out at different speeds, and we can see what happens. So let's go over here to generator. Here's my pickup coil. It's not connected to anything except a light bulb, and there's a magnet nearby. So when I turn on the water, it causes the paddle wheel to turn, and it causes, of course, the magnets to change. And so let's show the, oh, we don't want that. It's going to change the magnetic field that's passing through there, because sometimes north is passing through and sometimes south. Now, the light bulb is not very lit up right now because of the fact that, and I'm going to actually put the compass over here, we can see that the magnetic field strength is changing in time, and it's changing in direction. So it's not traveling very fast, it's not changing very much, and so that light bulb is not very bright. But if I make that magnet travel faster, the magnetic field is changing very rapidly through that coil, and it's going to induce more current in that loop, more voltage, and so the light bulb is going to turn on with a brighter amount, because it's inducing more current. So if you're at your homes and the electricity goes out and you decide to start your generator, essentially your generator is working on this principle. So a generator is actually opposite to a motor. So if you remember, an electric motor takes electrical energy and converts it into mechanical energy, rotation. A generator, on the other hand, takes mechanical energy, so it's taking this mechanical energy, potential energy of the water falling, converting it into rotational energy here. So it's taking mechanical energy and it's converting it into electrical energy. And the principle behind generators is electromagnetic induction. So we've learned that induced voltage can occur in a coil, and it can be increased by increasing the number of loops of wire in a coil. So if I change the number of loops in my pickup coil and I increase it, that will increase the voltage. I can also increase the speed of the magnet that's entering or leaving the loop, or how that magnet is changing, and that will also increase the voltage. It doesn't matter if the magnet is what's moving or the coil is what's moving. In all of these examples, it was the coil that was moving, it was the magnet that was moving, but it certainly could be the other way around. So Faraday's law of electromagnetic induction states that the induced voltage in a coil is proportional. The amount of voltage you get in a pickup coil is proportional to the number of loops that you have in the coil, and then it also depends on the rate at which the magnetic field is changing in time. The amount of current that's produced in the electromagnetic induction, so how much current you get through the light bulb, depends on the resistance of the coil. It also has to have a complete circuit, and it's going to depend on how much voltage is induced. There's a couple of demonstrations that we could look at that refer to electromagnetic induction. And so here are a couple of YouTube videos that are really nice that show this. We obviously, and I'm not going to go through and show the video inside of another video, but there's some other great videos that sort of show electromagnetic induction. So it turns out that electromagnetic induction is how we generate electricity. I mentioned earlier that an electric generator is basically the reverse of an electric motor. So what happens is that you can rotate a wire near a magnet and you can produce electrical current. And so here is an example in this picture here. This is a little simulation where we are generating electricity. So over here there's a handle where you can turn this handle, and as you turn the handle it's connected to this coil. The coil is set in a magnetic field, and so as this coil is rotated, you can see that there is a force exerted on that coil to rotate it. It produces a changing current, and the magnetic field that's passing through the coil is changing in time. And that's what this voltage is. It's going back and forth. It's just changing polarity as it goes around. So generators are going to be opposite of motors. I mentioned this earlier, converts mechanical energy, the rotation, into the electrical energy. If you've ever gone to a science museum, they often will have setups for electromagnetic induction where you can like get on a bicycle and you have to pedal the bicycle and try to light up a light bulb or turn on a radio or something like that. And so that process is essentially generating electricity through this process of electromagnetic induction. This is a picture of how the coil rotates in electromagnetic induction, and just sort of showing the green lines here are the magnetic field. And so as you rotate this coil, you have a lot of magnetic field passing through the coil, and then when the coil is flat, none of the magnetic field is actually passing through the center of the coil, and then it's going through again, and then it's not, and so on. And so when it rotates through one full cycle, you get one full cycle of AC, essentially alternating voltage. So it turns out that in our country, in the U.S., we generate power in this way. One way to do that is by using hydroelectric power. So in a hydroelectric power, similar to that other example with the Phet simulation, you basically have water that flows and it turns a turbine, and that turbine is then connected to coils or magnets. And as the coils turn in the presence of a magnetic field, it generates electricity. There's also something called the transformer that's here, and then from that we can then send out that electricity through the power lines and to our homes. We're going to talk about a transformer a little later, but the transformer is actually very important. So another interesting thing about power production is that very early on, when electromagnetic induction was sort of introduced, there was sort of a big debate as to whether or not we should use DC power or we should use AC power. And so Thomas Edison was very interested in using DC power, and there were some issues with that. There were short transmission distances. If you have DC, you have to have these power plants every couple of miles to get the power out to the homes. So you have to have these stations every couple miles. Westinghouse and actually Tesla, who is sort of the founder of electromagnetic induction, they were all for using AC power. And of course that won out. AC power is much more uniform in terms of getting the power to our homes. With DC, the farther you are from the power station, the less voltage that you would actually get, because there's so much resistance in the wires as it gets there. The other thing that's really important about using AC is we can use transformers, and we're going to talk about transformers. But transformers allows you to raise the voltage or lower the voltage at different locations along the transmission of the power. You can't do that with DC power. So essentially, once it leaves the power station, it is what it is, whatever that voltage is. And of course, as you get further down the line, you just lose some of that, versus the transformer, which can raise and lower the voltage. So when it leaves the power station, it's a high voltage, and then when it gets to your home, there's actually a transformer on the power line which reduces the voltage down. So we'll talk a little bit about how that works, but that principle works on electromagnetic induction, and you have to have AC power, or AC current and voltage.